Good morning, future presidents. Woo. So I'm a little worried today I'm going to lose my voice, so we'll see how long we can make it. So I'm going to cancel my office hours today because I'm not feeling very well. But we will struggle on today. So today we are changing topics. We are talking about thermal energy and the related topics of heat and temperature. So let's just go ahead and jump on in. So matter is made up of atoms. Okay. And often these atoms can be bound together in more complex combinations, which we call molecules. Okay, and molecules for, in terms of heat and temperature, can usually be thought of as single units, unless there are chemical reactions that are taking place. So we'll come back and talk about that in a second. So example, of course, is common molecule is water, H2O, which is two hydrogen atoms connected to an oxygen atom. So this whole unit is a water molecule. And in terms of matter, can usually be thought of as just a single unit unless it's undergoing a chemical reaction. Okay, in solids and liquids, these atoms and molecules are bound together by chemical bonds. Okay, so in solids and liquids, the atoms and molecules are bound together by chemical bonds. Okay, and these basically act like springs. So if you need a model of what matter looks like in the solid and liquid form, you could just think about a bunch of individual masses, molecules, that are bound together by a bunch of springs. So the springs provide restoring force, and they also keep the atoms bound together, but they also keep them from getting too close together. So they're just like a spring that will pull or push depending on how far apart the molecules are. So picture we're going to have here of a solid are just a bunch of molecules that are bound together by these little springs in between. Okay. And these molecules are constantly vibrating against their spring. They have energy, and so these things are constantly moving in this lattice. This is for a solid. For a liquid, it's a similar idea. The molecules are a little bit freer to move, but they're still bound to their neighbors and can vibrate back and forth against their neighbors. Okay, so each one of these molecules or atom, depending on what type of material it is, has both kinetic energy. Okay. That's the kinetic energy of the motion that it has against its neighbors, and it's got the potential energy. Potential energy comes from these bonds, the chemical bonds that are keeping it in solid or liquid form, okay, which is basically, like I said, acting like little springs that are attaching it to its neighbors. Okay, so each one of these molecules has kinetic energy and it has potential energy. Okay, so that is for a solid and liquid. For a gas, it's a little bit different. Okay, so in a gas, the chemical bonds between the atoms are basically negligible. So the molecules and the atoms in a gas are free to fly around and move. So the forces between the atoms and molecules are negligible. So that means they are free to fly around. Okay, so the fact that there's no forces between the neighbors means that all those springs are gone. And so the atoms just have kinetic energy, but they don't have any potential energy. So they're basically free to fly around however they like. Okay? So in a gas, the molecules have kinetic energy. Okay, but no potential energy. Or at least the potential energy between the molecules is so small that we can ignore it. Okay, so you can really think of them as free atoms and molecules. They're just flying around. Okay, so these atoms and molecules in solids, liquids, and gases, okay, they are individual masses. They are moving around. They have kinetic energy. All of them have kinetic energy. In a solid and a liquid, they have potential energy. And so the total of this atomic and molecular kinetic energy plus potential energy is just given a name which we've already used before. It's just the thermal energy. Okay. It's the energy of the microscopic motions in the solids and liquids and the gas. Okay. So that is separate from, for example, if we have this object, okay, and we gave it a motion, we gave it a speed, it would have a bulk kinetic energy, okay, and it has a potential energy. Okay, that's not the thermal energy. The thermal energy is the kinetic and potential energy at the microscopic level of the atoms and the molecules relative to each other, okay, not the bulk motion of the object itself. So thermal energy is the microscopic energy of the microscopic kinetic energy and potential energy. Okay, so we should be a little bit careful here because this thermal energy sounds a little bit at least the potential energy part of it sounds a little bit like chemical potential energy, which we have used before. I'm going to come over here, out of the way of that demo. Okay, we want to distinguish thermal energy from chemical potential energy. Okay. Chemical potential energy, so remember, potential energy means it's energy that's being stored. Chemical means that it's being stored by the chemical bonds. Okay. Chemical potential energy is energy stored in the chemical bonds holding molecules together. Okay, so that's actually the energy inside the molecule itself. Okay, not between the molecules that's binding them together. The chemical potential energy is the energy that's stored inside the molecule itself. Okay, and the chemical potential energy can only be accessed by changing the chemical bonds through some process like a chemical reaction, or like burning, for example, is a very common chemical reaction. So that should be distinguished by thermal energy, which does involve potential energy between atoms and molecules, okay? But the thermal energy is not changing the chemical nature of the material itself. Okay, so chemical potential energy can only be accessed by changing the chemical nature of the material that we're looking at. And the most common example we have of that is burning. So when you burn an object like gas or wood, you're changing chemical potential energy at the molecular scale into thermal energy inside the material. Okay, so energy. Energy is stored at the microscopic level, okay, in thermal energy. Okay, two very closely related concepts to thermal energy are heat and temperature. So we want to talk about these a little bit and distinguish them from thermal energy. They're all three concepts that are related, but they are not the same. We know intuitively if we take two objects and place them together, one of them is hot and one of them is cold, then there's going to be energy that is flowing between them. We're going to get a transfer of energy between them. So let's just draw that. We've got one object here with a high temperature, so this is what we would call hot. A second object, we're going to put it in contact with it with a low temperature, so what we would call cold. And we're going to talk a little bit more about what we actually mean by temperature in just a minute. Okay? But we know intuitively that if we take this hot object and this cold object and we put them next to each other, that there's going to be some transfer of the thermal energy from the one to the other. Okay, so the hotter one is going to get colder and the colder one is going to get hotter. Okay. This transfer of thermal energy we call heat. Okay, so heat is kind of like work. Heat is a transfer of thermal energy. It's a flow of thermal energy, but it's not thermal energy itself. Just like work is a transfer of kinetic energy or potential energy, okay, but it's not considered an energy by itself. Okay, it's a transfer of that. So heat, it's the flow of thermal energy from one object to another. Okay, so heat is, in this sense, heat and thermal energy are not the same thing. An object can have thermal energy, and heat is the transfer of thermal energy from one object to another. Okay? And intuitively, we know that heat will flow from a hotter object to a colder object. Okay? But we need to quantify that a little bit, what we mean by hotter object and colder object. Okay? And we do that by the definition of temperature. Okay, so before we get to a technical definition of temperature, let's just talk a little bit about what we intuitively know. Okay, temperature is our relative measure of how hot something is or how cold something is. Okay. Temperature, we know that if there's a temperature difference between two objects and you put them in touch with each other or in contact with each other, we intuitively know that heat will flow from the hotter object to the colder object. Okay, so heat will naturally flow from objects of higher temperature into objects of lower temperature. Okay, so temperature. Temperature tells us a direction. Temperature. Okay, unless we are doing some other type of work on a system, temperature tells us naturally which way heat will flow, okay, from hotter objects into colder objects. Okay, objects with higher temperature will lose their heat to objects at colder objects. Okay, so the additional point to make on this is if objects have the same temperature, then heat will not flow between them. Okay, and our term for this, there's another term for this, which is thermal equilibrium. These two objects are in thermal equilibrium, which means that heat does not naturally flow between them. Okay? And that is measured by their temperatures if they have the same temperature. And if we put two objects in touch with each other that have different temperatures, okay, eventually they're going to reach thermal equilibrium where they end up at the same temperature, okay, after we give enough time for the heat to flow from the hotter object to the cooler object. Okay, so I think we kind of have a good feel intuitively for what temperature is, okay, but we haven't yet defined it quantitatively. So what exactly is temperature? Okay? Our first guess might be that temperature is thermal energy, how much thermal energy an object holds. Okay? But that turns out to not be correct. It's on the right track. It's not quite what we mean by temperature. So is it just the thermal energy of a system? And the answer is no, not quite. Okay, so let's just think of a simple example for that. We can have two objects. Let's say one that is relatively small, and then one that is much larger. Okay? This one can be at a higher temperature. And this one at a lower temperature. Okay? But even though this one's at a lower temperature, because it's much larger, means that it can still have much larger internal energy. It has a lot more energy in it because it has a lot more molecules that are inside. Okay? So that means that in this system, we would still get heat flow from the smaller object to the larger object, even though this one has more thermal energy. Right? So the total thermal energy of the system isn't exactly what we mean when we're talking about the temperature. Okay? So let's think about this microscopically. What's going on at this interface between the high temperature object and the low temperature object? Okay, so here is the interface. Okay. Here is the high temperature object, and here is the low temperature object. Okay. And what we want to think about is how heat is flowing. Between these two objects. Okay. Remember, heat is the kinetic energy and the potential energy of the individual molecules. So on one side, we have the molecules of this object, which are flying around with some kinetic energy and potential energy. On the other side, we've got the other object. Okay. And when we say heat is flowing between them, what we mean is that these two are in contact and we're allowing microscopic collisions to occur. Okay? So heat flow is the result of microscopic collisions or molecular collisions. Okay? And then when we start thinking about this as a microscopic process, it becomes a lot more obvious what we mean by high temperature and low temperature. Okay? Because when we think about this in terms of individual molecules, okay, we know that energy will tend to be transferred from the high energy molecules to the low energy molecules when we have a collision. Okay? So when we have a bunch of these microscopic collisions going on, if these molecules have a higher energy on average than these molecules, then once they start colliding with each other, then the energy will tend to get transferred from the high energy molecules to the low energy molecules in those collisions. Okay, so in this sense, in fact, we have a very specific definition of temperature. Okay. Okay, temperature is, technically, it's a measure of the kinetic energy per molecule. Okay. And there is naturally going to be a heat transfer or a heat flow okay, which will occur when you have two sets of atoms, one with higher kinetic energy and one with lower kinetic energy. If we let them start colliding, there will naturally be energy transfer from the high energy molecules to the low energy molecules. Okay, so heat flow is a natural tendency for atoms or molecules to redistribute their kinetic energy equally. Okay, if you take a bunch of high kinetic energy molecules and a bunch of low kinetic energy molecules and you mix them all together, they're going to redistribute their energy roughly equally between them, which at a molecular level means that there is a transfer of heat from the high kinetic energy ones to low kinetic energy ones. So I have a little demo for that. So the same is true of macroscopic systems. Okay? Here I have a bowl that has a bunch of different balls in it. Okay, these are ping pong balls, which are very light. Okay, styrofoam balls, which are heavier than the ping pong balls. Okay, but they're still pretty light. Wooden balls, okay, which are much heavier. So these are the order from lightest to heaviest, and then super balls, so which are heavier than the wood. So think about these as a bunch of molecules of different masses that are put together in this bowl or in this one material. Okay? And I'm going to shake it up, so I'm going to give it energy. Okay? And naturally, these are all going to be colliding with each other. Okay? And so they've got kinetic energy, they're sharing it, and they're passing it back and forth between each other. Okay? But the fact is that since some of them are very much lighter than the other ones, okay, if they've all got the same kinetic energy, or roughly the same kinetic energy, then the lighter ones or the ones that are less massive, have to have a much higher velocity, right? Remember, the kinetic energy is 1/2 the mass times the square of the speed. So if these all have roughly the same kinetic energy, the low mass ones are going to have a much higher velocity or much higher speed in order to have the same kinetic energy. Okay? So let's put these all together, and let's just start shaking them. I haven't done this one for a while, so let's see how this works. So I'm just going to start shaking it, and what we'll see is that the molecules, or the balls with the highest speed, should be jumping out of this faster than the ones with the lower speeds. Okay, so you can see, let me do that again. You can see, actually, if you look on the ground down here, that all the styrofoam and all the ping pong balls have jumped out of there. Okay, those are the low mass ones. Okay? When they are sharing kinetic energy with the other ones, they got a much higher speed. Okay? And then the heavier ones, I see one super ball down here. Oh, thank you. And there's one wooden ball down there. Okay, okay, thanks. But the rest of them stayed inside of the bowl. So let me try that one more time, for those of you who are asleep. Okay, so remember, lightest, okay, and the heaviest. Okay, so, yay, there we go, light, light, light. Got one heavy one there. Okay, that's a lot of fun. You guys can do that one at home. Thanks. Thank you. Cool, okay, thanks. So you see, when they're sharing their kinetic energy, so naturally you take a lot of objects, you let them start colliding with each other, and they will naturally distribute their kinetic energy so those are equal. Okay? So that's all the temperature is. At the microscopic level, it's just the natural tendency for molecules when they are colliding with each other to share their kinetic energy equally. Okay? So temperature is a measure of the kinetic energy at the microscopic scale. That tells us something actually immediately about temperature. Since temperature is a measure of the average kinetic energy, we know that if all the molecules are sitting at rest, then the average kinetic energy is 0, which means that there must be a 0 temperature, a lowest temperature, okay, which we call absolute 0. So, the fact that temperature measures average kinetic energy tells us that immediately that there is a lowest temperature we can reach. Okay, and that's where the kinetic energy for the molecules goes to 0. Okay, so that tells us that the motion of the molecules or the atoms inside whatever object we're looking at must stop. So I won't stress this too much here. We'll come back to this later in the semester. This actually turns out this is a prediction of classical mechanics, but quantum mechanics actually tells us this can't be true. Okay? But for now, let's ignore that. And there's still an absolute zero for the temperature scale. Okay. Quantum mechanics will tell us that things can't be absolutely at rest ever. Okay? But classically, that means everything must come to a stop, and all the molecules and atoms must be at rest. So let's write down some just common temperatures in 3 different temperature scales, just for reference. Okay, so there are 3 common temperature scales that we use. Okay, so we, in the US, commonly use Fahrenheit when we're talking about, especially when we're talking about weather or temperatures in a room. Okay. Most places in the world use Celsius, okay, which is the metric temperature. And most scientists use a Kelvin, a scale called the Kelvin scale, which takes into account that there's an absolute zero. So it starts with 0 at absolute 0. Okay? So, but otherwise it's very similar to the Celsius scale. So let's write down some common temperatures here. So, well, absolute 0 isn't so common, but that's the lowest temperature we can reach. Freezing water, room temperature, body temperature, and then finally boiling water will be our last one. Okay, so let's look at those in 3 different temperature scales. So there's Kelvin, which is the one that we use mostly scientifically, Celsius, which is the metric scale, and Fahrenheit. Okay, so absolute 0, easiest on the Kelvin scale, it is 0. Okay? On the Celsius scale, that is minus 273 degrees. And on the Fahrenheit scale, that's minus 460 degrees. Okay? So this we would call degrees Kelvin, degrees Celsius, and degrees Fahrenheit. Thank you. That's right. We don't use degrees on Kelvin. Thank you. Okay, so 0 Kelvin, minus 273 degrees Celsius, and minus 460 degrees Fahrenheit. For freezing water, for Kelvin, it's 273. Okay, for Celsius, it's easy. That's the definition for freezing water. Is the definition for 0 for Celsius. Okay. Fahrenheit, it's minus 32 degrees. Sorry, 32 degrees. Okay, thank you. Okay, so room temperature is roughly 70 degrees Fahrenheit. Okay, it's 21 degrees Celsius, and that is 294 degrees Kelvin. And let's see, body temperature, we know it's 98.6. Okay, in Fahrenheit, that is 36 degrees Celsius and 309 in Kelvin. And then finally, boiling water is defined as 100 degrees in Celsius. That is 212 in Fahrenheit and 373 in Kelvin. Okay, so I don't want you guys to necessarily memorize all these or be able to switch between them. So, but it's good to have a good sense for what some of these numbers are outside of just our basic numbers for Fahrenheit. Okay, so before we move on, we are going to have a quiz, which we haven't had for a while. I know, very exciting, isn't it? Okay, can I have the projector on? Hey, why don't you ask me your questions on Thursday when I'm a little more awake? We're good? Stuff's going very good today. Okay. Who doesn't have a quiz sheet? Raise your hand. Oh, you guys came very prepared today. Good job. Okay, let's go ahead and get started then. So, question number 1. The maximum speed a rocket can achieve is A, the speed of sound, B, equal to the speed of its exhaust plume, which we called the exhaust speed, C, less than the speed of its exhaust plume, which we called the exhaust speed, or D, greater than the speed of its exhaust plume, the exhaust speed, but less than the speed of light. That's a good question. I don't think they have time. I think they have time to look anything up. I thought about it, so I don't think they have time to look stuff up anyway. Oh well. Okay, let's move on. Question number 2. Suppose you have an aquarium and you notice that you have a solid plastic decoration and a rock of the same volume, but the rock is twice as dense. So you've got the two objects, the plastic decoration, the rock. They're the same volume, but the rock is twice as dense. Okay? Both are totally submerged in the water. The buoyant force on the plastic object is about blank as that on the rock. So the buoyant force is twice as big, A, B, the same, C, half as big, or D, 1/4 as big. Okay, let's pass those over to the sides, and the GSIs will come up and pick those up. Okay, so let's pick back up here. So okay, so we're going to start talking now about heat capacity. So, conceptually, we know that if we add heat to an object, we are going to start increasing its temperature. So the heat capacity is a relationship between the amount of heat we've added, okay, so the amount of thermal energy we've transferred to an object, and the change in the temperature of that object. So heat capacity is specifically defined as the heat required per 1 degree temperature increase. Okay, so that's for a given object. So the amount of heat we have to transfer to the object in order to increase its temperature by 1 degree. And so, of course, if we keep adding heat to the object, it's going to keep increasing its temperature. Okay, so we could keep adding heat indefinitely, and the temperature would keep going up. And so that's why we define the heat capacity as the heat required for each degree of temperature increase. Right? So conceptually, we know this must depend on the mass of the object, right? So the more massive an object is, the more heat that's going to be required in order to raise its temperature by 1 degree. Okay? So, but it also depends, or it might depend, turns out it does depend, on the composition of the object. So different types of materials require a different amount of heat to raise their temperature by a specific amount. Okay? So in order to take into account the differences between materials, we define a second quantity, which is the heat capacity per unit mass. And we call this the specific heat that's just the heat capacity for a given object divided by its mass. Okay? And so this takes into account just the difference between materials, so not the mass of the object. So, water and lead will have, if you take into account that you have equal masses, so we don't have the difference in the mass, we'll still have a difference in their heat capacity, okay, because their specific heats are different for the given materials. Okay, so, and it turns out that materials can vary quite dramatically in their specific heats. Let's just do another little table with different types of materials, just so we can see how much this can vary. Okay, so for this table, I'm going to use the standard metric unit of joules per kilogram per degree Celsius, but I don't want you to even worry about these units at all. I really want you just to see how much the heat capacity can vary between different types of materials, okay? And that just happens to be the units that we're we're writing this in. So for lead, it's specific heat. So once we've taken out the mass, so this is just per unit mass, is 128 joules per kilogram per degree Celsius. Okay? And this table is going to go in increasing order. So for steel, it's 460. You can already see a big jump, okay, just between lead and steel. They're both metals, but steel can hold almost 4 times as much, 4 times as much heat for each degree in temperature. Okay. Glass is 840. Aluminum is 900. Okay, so you can see we're almost a factor of roughly 8, 7.5 above lead. Let's see, what else do I want to add on there? Air is 1,001. And then, let me see, the last one I think I'll put on there is a really important one. Water. Water has a specific heat, a whopping 4,190. So 30-something times more than lead. Okay. So there are 2 ways of interpreting specific heat. And those 2 ways are, first off, to think about the larger one. So the larger the specific heat, the more thermal energy that the material holds. So for example, water has a huge specific heat compared to most materials, which means that for a given increase in its temperature, it can hold a lot more energy. Okay? And so, for example, oceans. The oceans, when they heat up in the sunlight, right? So if they heat up to a few degrees, heating them up requires a lot more energy, okay? Which means the water is holding a lot of energy. Okay? So that's why, for example, hurricanes form over the oceans. Okay? As the water cools, it releases a lot of energy, okay? Because it's holding a lot of energy because it has a very large specific heat. Okay, so water can hold a lot of thermal energy compared to other materials. Okay? So the other way to think about it is that the smaller the specific heat, okay, the easier it is to heat up a material. Okay? So that's why, for example, if you have a metal spoon, metals tend to have relatively low specific heats, and you put it in a hot cup of coffee, then your spoon will heat up very quickly. Okay? And the reason for that is that it only takes a relatively small amount of energy being transferred from the coffee, which is basically water, okay, to the spoon in order to heat up that spoon. Okay? So large specific heats you can think of as it can hold a lot of energy. Small specific heats, I think it means that that material can heat up very, very easily. It doesn't take very much thermal energy to make that material very hot. Okay, so the specific heats also tells us what happens when we bring 2 objects together. So we know if we've got 2 objects and we at different temperatures and we put them in contact with each other, there's going to be heat that flows between them. Okay? The heat will flow until they have the same temperature, okay? But what that final temperature is will depend on the specific heats of the material. For example, if you take a lead ball and drop it into water, okay? Then, for example, if we had a small lead ball and we dropped it into a big container of really hot water, say, then there's going to be a heat flow from the hot water to the colder lead ball. Okay? But the lead ball is going to heat up very quickly, or it doesn't take very much energy in order to heat that up because it has such a small specific heat, okay, which means that the final temperature is going to be a lot closer to the hotter water than it is to the smaller lead ball, if that makes sense. So when you bring two objects together, there's going to be a heat flow between them, and their final temperature will depend on those specific heats of the materials. Okay, so let me do a quick demo about the heat capacity. Uh-huh. So the question is, if the lead ball is dropped in the water, when the lead ball heats up, does the water cool down? Is that right? Yes, absolutely, absolutely. So so for that example, let me just draw a picture of that. So if we take that, right. So let's say we have water there. Let's say it's close to boiling, so it's about 100 degrees Celsius, right? So we got a hot container of water there, and we're going to take this lead ball and drop it in here. So this is lead, and let's say it started off at a smaller temperature. Okay. So there's definitely going to be a heat flow from that water into the lead. Okay? So the fact that heat is leaving the water means that the water is cooling down. Okay? At the same time, the heat flow into the lead means the lead's heating up. Okay? And so for the specific heat, or specifically we have to take into account the mass. So the heat capacities tells us, so it's the heat required for 1 degree temperature change, right? So heat will flow into that lead and that means that the water is cooling down and the lead is heating up until they reach the same temperature. And then at that point, no heat will flow because they're in thermal equilibrium. So all their molecules have, on average, the same kinetic energy, right? So heat that flows out of the water is going to be cooling the water down, and the lead is going to be heating up. Okay? So the point about the heat capacities was because lead has such a small specific heat, it means it doesn't take very much energy to heat it up. So the lead will heat up relatively easily compared to other materials, and so the water will cool down, but it won't cool down very much. Okay? So if we take in another, like an aluminum, right, and we put the same massive aluminum ball in the water, then it takes 7 or 8 times as much energy for it to heat up, which means that the water had to lose much more energy to get it to the same temperature, which means that the final temperature of the system would be lower if we had taken an aluminum ball and stuck it in here than the lead ball. Does that make sense? Somewhat? Uh-huh. Sorry, can you say that one more time? Uh-huh. Okay. So the question is, for the aluminum ball, why does it take more energy than the lead ball? So this is just a difference in the basic properties of the material. So lead, because it has a specific heat, that tells you how much energy it takes for each degree change in temperature. And it has a factor of, let's say this is 7 or 8, right, below aluminum, which means it takes almost 7 or 8 times as much energy to heat up the same amount of aluminum as it does for lead. And that's just basic material properties between them. So that means that if you take a certain amount of heat and you transfer it into the lead ball, its temperature is going to go up 7 or 8 more times than if you take the same amount of heat and put it into the aluminum ball. Right? And so if we dropped aluminum in here, it would just take, it would take longer for it to transfer energy, and it would require more energy transfer for it to reach the same temperature as the water. And at the same time, as the heat is leaking out of the water into the ball, then the water is going to be cooling down as well. So ask me later if that doesn't make sense. Okay. Okay, so let's look at an example of this. Hopefully this is hot enough. Okay, so I have got here, this is just a thin sheet of wax. Okay. We all know what happens to wax when you heat it up. It melts. Okay. And what I've got here is a pot of water that's been simmering the whole class. And I have this nifty little gadget here. Okay, so I've got 5 different types of balls in here. They're all the same size. There's lead, glass, zinc, brass, and iron. Okay, and these are all the same size. I'm going to put them on the lead ball. I mean on the lead plate. Okay, but they all differ quite dramatically in terms of their heat capacity, how much heat they can store. Okay? So the fact that they're all in the same pot of water here means that they've all got about the same temperature, about 100 degrees Celsius. Okay? They've all been simmering at the same amount, for the whole class. So they've all got about the same temperature, 100 degrees Celsius. But the amount of thermal energy that they store is quite dramatically different between the different materials. Okay? So I'm just going to take them and set them on this plate, this wax plate. Okay, so we've got lead, glass, zinc, brass, and iron. And let's just give them some time for their heat to transfer. Okay, there's the brass one. There's the iron. Okay, let's see. Let me turn that a little bit. So iron went through, brass went through. The zinc looks like it is stalled out about halfway through. The glass marble has barely made a dent at all in the wax. The lead has sunk down a little bit, but not nearly as much as the zinc did. Okay? So this is demonstrating the difference in the heat capacities between the materials. So the iron and the brass, okay, even though these all were the same temperature, ow, it's hot. The iron and the brass have a lot higher heat capacity. Okay? The specific heat actually isn't even that much, so iron is basically the same as steel. Okay? But remember, that's per unit mass, and then steel has a very high density, so the heat capacity is very large. Okay? Glass actually has a higher specific heat than steel, but it's not nearly as dense, and so the heat capacity is very small. Okay? So the ones that had the very large heat capacity had a lot more heat in order to transfer to the wax, in order to melt all the way through. Okay? Whereas, for example, the glass has such a small heat capacity that the amount of thermal energy that it holds was so small that it didn't even make a dent in that wax sheet. Okay, so let's talk briefly about heat transfer. Okay, let me get this going while I'm talking. really shouldn't be playing with fire today, but that's okay. A little too groggy for that. Okay, so heat transfer. This is, there are different physical ways that heat can actually flow or be transferred between objects, and let's just talk about those. Okay, it's physically how heat flows. So the one that we've been seeing so far is called conduction. Conduction is transfer of heat between two objects when we physically just put them in contact with each other. Okay? So it's the transfer of heat through molecular collisions. Okay, but there is no material movement. Okay, when I put my hand on the table, right, I'm transferring heat by conduction to the table, okay? But the molecules in my hand are still staying in my hand. The molecules in the table are staying in the table. There is molecular collisions between them, okay? But there's no transport of actual material between the two objects. Okay, that's conduction. The next one is convection. Okay, convection, which is heat transfer through bulk motion. Okay, so heat is being transferred because material itself is moving. So the examples of that are, of course, wind. Wind is the most common example of convection, where, for example, you can have a hot wind coming in and heating up an area as it blows through. Okay, that's convection. Or likewise, a cool breeze comes through. It cools down by moving air in, colder air through. So there is wind, ocean currents, and drafty rooms. Okay, so I have a little demo here of convection. So this has been heating up while we have been talking. Okay, there we go. So I've had the Bunsen burner basically heating up this one corner of this tube. So this tube is filled with water. Okay. So there is certainly conduction that's going on. I'm heating up this one corner, and the heat is being transferred to the rest of the water. Okay? But more importantly, there is convection going on. Okay, so it happens in, you know, if this was filled with air, they would be moving in some sort of circular pattern here. But the same is true for liquids. Okay, liquids are free to move, so there can be bulk movement of material. And this is going to be hopefully more obvious when I put in a little dye into this. Okay. You can see that the blue there is starting to move around. Okay. That's because there is a net convection of heat from this corner moving around in the circular pattern. So heat is being convected all the way around this circle, okay, trying to keep the water uniformly heated up there. I don't know how well that would show up on that video. It's not an overly dramatic thing. And pretty soon this will all be blue from the water moving around in a circle. Okay, convection. So convection is the bulk motion. Okay, it's a transfer of heat because the material itself is moving, not just from the molecular collisions themselves. Okay, so, and then, let me turn that off for a second. The third example, which we're going to talk about a lot more in in the next lecture. Okay, the third is radiation. Radiation. Okay, so radiation is heat transfer through the emission of light. Okay, so you feel radiation heating every time you walk out on a sunny day, and you can feel the sunlight heating up your face. Okay? Likewise, when you're standing in front of a campfire, usually a lot of the heat in the air is being convected upwards. You still feel heat coming from the radiation, from the light being emitted in the campfire, and specifically infrared light, which we will talk about more in the next class. Okay, so like I said, so we'll come back and talk more about radiation and conduction in the next lecture. I am about to give out up here, so I think I'm going to end the lecture now before I absolutely collapse, and we will pick up here next time.